Okay, so this still we try to apply the Gauss law for the planar symmetry. Okay, so just now we have a single plane. Okay, a single plane. Here we try to have two conducting plates. Okay, try to have two conducting plates. So what it means is that okay, we have one conducting plate here. Okay, another one is here. Okay, there is a positive charge. Okay, there's positive charge on the left one. Okay, so and yeah. Okay, so it should be like okay, these two are independent. Okay, these two are independent figures. Okay, so here what it really means is that okay, first by considering okay, this is a conducting. Okay, this is a conducting plate. Okay, and we still assume it has some thickness. Okay, so half of the charge will go to the left side, and then the half of the other charge will go to the right side. So on each side, the surface charge density are sigma 1. Okay, are sigma 1. Okay, so actually it will generate E plus. Okay, E plus to be I mean what I mean is this is E plus. This is E plus. Okay, so E plus will be sigma 1 over 2 epsilon naught. Okay, because it generates the E field on both sides, so there will be this one half factor here. Okay, this one half factor because it generates the E field on both sides. Okay, generate the E field on both sides. So if you don't believe, you can try to, let's say, assume a Gaussian surface. Okay, also a cylinder, but this is a cross section, so you only see a rectangle. Okay, so on this side you will have E times A here. This side you also have E times A here, but you don't have anything for the top and bottom. So finally you will get a epsilon naught times 2EA equals sigma A. Okay, sigma A. So it turns out to be something like that. Okay, this is sigma 1. Okay, sigma 1, like this. Okay, like this. Yeah. Okay, so we have E plus, and then similarly, if we have a negative charge, E1. Okay, sorry, E1. EI will be sigma 1 over 2 2 epsilon naught. Here we try to play these two plane with the same amount of charge and then with opposite side, and then place it close together so that all the charge will concentrate to the closer surface. Okay, so for positive charge will be on the right surface, and then the negative charge will be near the left surface. So which means that we both have 2 sigma 1. Okay, on both surfaces. Yeah, because all the charge, okay, originally sigma 1, okay, so finally here we have 2 sigma 1 for the density, for the surface charge density. So which means that the E plus turns out to be 2 with a factor of 2. Yeah, because we replace this 2 sigma we replace this sigma 1 by 2 sigma 1. Okay, so turns out to be like this. Okay, we replace this as this one. Okay, this one. Okay, so similarly here. Okay, but the idea here is like for the left one it generate E plus. Okay, E plus pointing to the right side, and then E plus pointing to the left side on the left side, and then this part also E plus pointing to the right side. Then for the E minus, actually it's a negative charge, so E field points to the right side. Okay, on the left, E field point to the right side on the left, and then E field point to the right side, the left side on the right. Yeah, so you can see So you can see this one and this one cancel. This one and this one cancel. But for these two, they add up together. They point to the same direction with the same amount of E field. So for the middle part, we have E equals E plus E minus, okay, which will be 2 times of this, okay, because this one and this one are the same. So adds up to be 2 sigma 1 over epsilon naught. And then we call the new surface charge density of sigma to be 2 sigma 1, okay? So we don't try to use sigma 1 anymore. So it turns out to be sigma over epsilon naught, which is again a constant, okay? So actually, I think this kind of, the discussion is quite messy. But so actually you can just focus on the conclusion here. E is a constant, okay? It's only proportional to the surface charge density, okay? Only related to the surface charge density, proportional to the surface charge density. And then epsilon naught is a constant, the permittivity constant. Yeah, so actually this structure is the capacitor. Okay, we will learn more about that in chapter 25, okay? But anyway, here we have a sample problem about this, okay, Okay, so here, let's see. Okay, the portion of two large parallel non-conducting sheet, okay, two large parallel non-conducting. Okay, each with a fixed uniform charge on one side, okay? So the magnitudes of the surface charge density, sigma plus and then sigma minus, are not the same, okay? This is 6.8, this is 4.3. Yeah, so for the negatively charged, okay, so find the electric field to the left of the sheets, okay, to the left, okay, and then between, and then to the right, okay. So first we try to calculate E plus, okay, generated by the positive plate, so which is sigma plus, okay, over epsilon naught, so which is 6.8 times 10 to negative 6. Micro is 10 to negative 6, and then 2 times 8.85 times 10 to negative 12. So which is 3.84 times 10 to the 5th Newton per Coulomb. And then E minus will be sigma minus over epsilon naught, which is 4.3 times 10 to negative 6 over 2 times 8.85 times 10 to negative 12. Okay, so this is 2.43 times 10 to the 5th Newton per Coulomb. Okay, so actually we have E plus, okay, point to the left side on the left, point to the right side on the right, and then E minus, point to the right side on the left, point to the left side on the right. Okay, so on the left side, E left, okay, will be, okay, this one and this one cancel, partly cancel. So E plus minus E minus, okay, which is 1.41 times 10 to the 5th, okay, so by subtracting these two. Okay, so and then EB in the middle, okay, so they are subtract, they are adding up, okay. So it should be E plus E minus, so which will be 6.27 times 10 to the 5th power Newton per Coulomb. Yeah, and then finally ER is also E plus minus E minus, okay, which is again 1.41 times 10 to the 5th power N over C. Okay, so as much as we can see, this one point to the left side, this one point to the right side, this one also point to the right side. Yeah, according to this figure, okay, you can see that, E plus is larger, has a larger magnitude, so E plus determine the direction. Okay, so I think this one is quite straightforward. Just use the sigma over epsilon naught. Okay, and then you plug in a number, and then finally you add up. Yeah. Okay. So here is the last case, is the applying Gauss law for the spherical symmetry. Okay, for the spherical symmetry. Okay, so here we try to recall the shell theorem. Okay, so if you still remember, okay, we have mentioned the shell theorem, but at that time I just told you that try to believe it is true. Okay, at that time we don't have sufficient knowledge to understand why it is true. So here, by using the Gauss law, we will be able to understand why it is like that. Okay, so if you still remember, the shell theorem have two so have shell theorem 21.1. Okay, so have two statements. Okay, so first statement is that a shell of uniform charge attract or repel a charged particle that is outside. Okay, outside. Okay, so the first statement relates to the outside part. The shell as if all the shell charge were concentrated at the center of the shell. Okay， 就是如果你有一个球壳，它有电荷均匀的分布在表面，或者是一个球啊，均匀分布在它里面啊。如果你找那个外面的一点的话，那它就可以看成所有的电荷都集中在中心的位置。Okay, like this. Okay, so actually this is a sphere. The case for a sphere. Okay, so this is the sphere of charge. Sphere of charge. Okay, all the charge are concentrated here. Yeah, so or actually distribute uniformly distribute along the sphere. Yeah, so so it actually means that if we consider any point outside, okay, so here we try to assume S2 as the Gaussian surface with a larger radius, okay, than the radius of the sphere. So here applying the Gauss law for S2, which will be like epsilon naught integration of E dot dA equals Q enclosed is actually Q. Okay, Q here. It's actually Q. So according to what we have done before, you will have epsilon naught, and then times E is uniform, and then the surface area of a sphere is 4 pi r square. Okay, if you still remember, equals Q. Okay, so it turns out to be like that. Okay, so as much as it has a spherical symmetry, 球形对称. Okay, so actually we can simplify this surface integral easily as this one. Okay, and then it turns out to be something like that. And then this one is actually like if we just put all the charge in the center. Okay, so and then here we have this R. Okay, so the E field here is actually the same expression. Okay, and then for the second statement, if the charged particle is located inside, okay, inside a shell of theorem charge, a shell of uniform charge, there is no electrostatic force. Okay, no E field. What it means is that, okay, here we try to assume S1. S1 is has a smaller radius, okay, than the radius of the sphere. Okay, so here by applying the Gauss law for the S1, Yeah, it actually encloses no charge. Okay, so epsilon naught integration of E dot dA is actually zero. It's actually zero. So this is not zero. Okay, this turns out to be E to be zero. Okay, yeah, so just it is symmetry. It is symmetry. So all the point must be E equals zero. Must be E equals zero. It cannot be the case that a part of it is positive, parts of it are negative, and then they cancel each other. It cannot be like that because it is symmetry. So E field should be uniform over the whole surface of S1. Okay, so this is the two shell theorem. Okay, so as much as we have Gauss law, okay, we can skip through the complicated computation, okay, and then come up with these two conclusions. Yeah, so here we try to extend it a bit. Okay, so make it like, okay, we have charge distribute uniformly in the sphere. Okay, not only on the surface but also inside the sphere. Okay, so here if we consider outside the sphere, it still has the same as expression. Okay, so it's just like all the charge are concentrated inside. Okay, just repeat the same step. Okay, for the top part of this page. Okay, but if it is inside the sphere, okay, we need to calculate a bit. Okay, here what it means is that, okay, see here we have a uniform volume charge density. Okay, so this is actually rho. Okay, as much as it is uniform. Okay, it is uniform, so it will be like rho will be the total charge. Okay, the total charge in the sphere divided by the volume. Okay, the volume of a sphere is pi over 3. 4 over 3 pi r cube. Okay, this is the volume. Okay, actually, I hope you have learned it in high school mathematical class. Okay, or maybe a calculus class tells you, okay, how to rotate a circle so that okay, it encloses a volume like this. Okay. Okay, actually, this is the volume of a sphere. Okay, or here we try to assume a Gaussian surface. Okay, because we try to find the E field inside the sphere. So here we try to have a Gaussian surface with a radius smaller than the radius of the sphere. So here, of course, if we try to apply the Gauss law for this Gaussian surface, we must consider the Q enclosed. So the Q enclosed will be like 4 over 3 pi small r cube. Okay, so this is considered partially, but as much as the volume charge density is uniform, so these two must be the same. Okay, and then here we try to cancel like 4, 3 pi can be cancelled. So here we try to have Q enclosed, and then we move this r cube to the left side, and then we swap left and right. So we have a Q enclosed equals small r cube over capital R cube times Q. Okay, by manipulate this one. Okay, so we can try to solve a Q enclosed like this. Yeah. Okay, so we can get this one. So here, actually Q enclosed is ready, so we can try to apply Gauss law for this Gaussian surface. So this is what we face for millions of times. So it is like epsilon naught E times 4 pi r squared. So it is a sphere. Yeah, so Q enclosed is this one. Okay, we put it here. Then we can try to cancel this r cube and r squared. Okay, r squared and r cube. The other stuff cannot be cancelled. So here we have 4 pi epsilon naught goes to here, and then we have r goes to here, q goes to here, and then finally r cube, capital R cube goes to here. So this is an interesting expression. So of course this is a constant. This is the total charge amount of the sphere, okay? And then this is the radius of the sphere, okay? So it turns out to be proportional to the radius, okay? It is proportional to the radius. Yeah, so this is a very, very interesting expression. So based on those two formula, outside it is this one, and then inside it is this one. So actually we can try to plot it. Okay, the x-axis is the r-axis, and then the y-axis is E. Okay, so we can try to plot E here, and then in terms of R. Okay, so for the top one, it is R is larger than or equal to capital R. For the bottom formula is R smaller than capital R. So actually they will meet at this point. Okay, which means that if we plug in R to be capital R, so E will be Q over 4 pi epsilon naught capital R squared. Okay, and then if this part is R is smaller than capital R, it is linear increase. Okay, linear increase. This part is linear. Okay, but for this part, okay, or maybe I can write it as this is proportional to R, and then this is proportional to 1 over R squared, or inversely proportional to R squared. Yeah. Okay. Okay, so far any questions? Okay, so let's move on. So this is the very, very challenging additional examples I would like to show. So actually, it actually says what is the it says the volume charge density of a solid non-conducting sphere of radius r, capital R, with radial distance r as given by rho. Okay, so this is the charge density. Okay, which is not uniform. Okay, this case the charge density is uniform. This is not uniform. Okay, so that we need to use some integration. Okay, so with this density, this is proportional to the radius. Okay, so it asks what is the sphere's total charge. Okay, so actually for this total charge, we need to do the triple integral of the rho and the V. Okay, V means the volume. Okay, capital A means the area. Okay, so A is like a double integral. So this integration of dV is like a triple integral because we need to integrate rho in a three-dimensional. Okay, for the sphere. Okay, so actually we need to use the spherical coordinate. Spherical coordinate. Okay, so the spherical coordinate would be like integration of 2 pi integration from 0 to pi, and then the integration from 0 to capital R. and then we put the rho here. Okay, you may ask what it means. Or maybe I should put all this thing in. Okay, so the rho will be like this is let's say this one is rho s. Okay, rho s times r over capital R. Okay, we try to denote this 35.4 picocoulomb per meter as rho s. Okay, so that we don't need to write too much. Okay, so this is rho equals this thing. Okay, so rho will be like a rho s times R over capital R. Okay, so this is rho. So what is dV in the spherical coordinate? dV in the spherical coordinate will be like R squared sine of theta dr d theta d phi. Okay, you may ask, okay, what is this stuff? Okay, so let me simply tell you that. Okay, so as much as we have x, y, and z axis like that. Okay, so as much as we have a point R, okay, a point, we try to express this point rather than using x, y, z. Okay, we try to use r, theta, and phi. R, theta, and phi. Okay, so you can see, okay, phi is from 0 to 2 pi. Okay, what it means is that we try to project this point on the xy plane. Okay, let's say point project to here. Okay, so this is the xy plane, and then we try to connect it like this. Okay, and then this is r. Okay, the r is the distance of this point from the origin. Okay, so this is r. And so this is theta. This is theta, or somehow the theta should be like let me see. Okay, so y. Okay, so the theta will be like let me see. Okay, the theta will be like from the negative z-axis to here. Okay, to here. This is theta. Okay, and then here we try to this is on the xy plane, and then this is the phi. Okay, this is the phi. So the phi can actually goes from this is phi equals 0, and then goes for the whole round. Okay, which will be from 0 to 2 pi. So that's why you can see d phi is from 0 to 2 pi. But the theta can be at most from here is theta equals 0, and then here is theta equals 180 degree or pi. Okay, theta equals pi here. Okay, so going from here to there. Okay, so you can see d theta will be from 0 to pi. And then dr, okay, and then dr is nothing special, is here. But of course you may ask why we have this stuff. Okay, when you learn calculus, you will know that, okay, you actually need to remember this. Okay, this one is coming from something called the Jacobian matrix. Jacobian matrix. It is like something like the change of variable. Okay, multi-variable, and then you like to change a variable, then you will have a Jacobian matrix to see. Okay, we have a factor like this. Okay, so that's as much as we change from dx, dy, dz, and then okay, we change it to r theta phi direction. Okay, we need to come up with this one. But simply speaking, you can consider something like this. Okay, if we try to change the r, dr will be like this. Okay, and then here, okay, you can see. Okay, that will be a small dv. Okay, small dv. that turns out to be something like this. So it will be like some dr times some r outside of theta. Okay, outside of theta, and then r outside of theta, and then yeah, that will be something like that. Yeah, will be something like this. So as much as you try to change, okay, this will be d phi, this will be d phi. Okay, so this will be r d phi. Okay, I mean r d theta, and then this part will be r d phi and then sine of theta. Okay, d phi. Okay, so it turns out to be something like that. Okay, so yeah, it would be like a geometric shape. Okay, if you're familiar, if you are interested in it, you can try to check it out on the Wikipedia or for the spherical coordinate. But actually here, yeah, according to my experience when I learned the calculus, multi-variable calculus, it will be better to memorize this factor, yeah, because it will occur very frequently. Okay, so actually this triple integral looks very horrible, but actually all the variables are separable. So the integration is actually very easy. So let's say rho s and r are constant, so we can move it to the front. And then we actually have r and r squared here. So it turns out to be r cubed dr, integrate from 0 to capital R. And then next one is this one is sine of theta d theta. Okay, so sine of theta d theta will be like integration of sine of theta d theta from 0 to pi. So the final part is d phi. Okay, sorry, this should be theta. Okay, and then finally d phi. Okay, we don't find any phi anywhere, so actually it's like integrating a 1. Okay, and usually I just skip this one. Okay, of course you can actually write it as integration of 2 pi and then 1 d phi. Okay, it is still correct. Okay, but yeah, usually we will try to write it like this. So actually we separate this triple integral into 3 independent single variable integral. So it turns out to be rho over r, rho s over r. And then this one is r to the 4th power over 4. Okay, very easy. And then this one is actually 2. Okay, why is it like that? Okay, it is negative cosine of theta, evaluated from 0 to pi. So it turns out to be 2. And then final part, okay, integrating 1 from 0 to 2 pi is actually 2 pi. So yeah, so turns out to be like pi rho s r cubed. So this is the case if the rho, the volume charge density, is proportional to the radius. The total charge will be something like this. And of course, you can actually plug in the number. Okay, pi is 3.14, and then times rho s is 35.4 times 10 to negative 12. Okay, pico is 10 to negative 12. And then times the radius is 5.6 centimeter, 0.056 cube, which is 1.95 femtocoulomb. Okay, femto is 10 to negative 15. 10 to negative 15 here. Okay, so this is only the first question. Okay, we still have B, C, D, E. Yeah, for question B, okay, what is the field magnitude of R equals 0? R equals 0 will be E equals 0. E equals 0, yeah, because yeah, actually you have some charge. Okay, you try to draw a very, very small try to draw a very small Gaussian surface, you enclose almost nothing. Okay, you enclose almost nothing. Okay, so the E field enclosing almost nothing. Okay, it turns out to be E to be 0. So for the question B, it is nothing. Okay, it is nothing. Yeah, so for question C, okay, what is E field at R equals capital R over 3? Okay, so that is inside the sphere. Okay, so here we need to compute the Q enclosed again. Okay, Q enclosed. So actually, it will be similar to this one. The only different thing is that we try to change this R into R over 3, and then this is pretty much about it. Yeah, so this is nothing but rho s over capital R integration of R cubed dr from R over 0 to R over 3, and then integration of sine theta d theta from 0 to pi, and then integration of d phi from 0 to 2 pi. Okay, so this is easy. Rho s over R, this is R to the R over 3 to the 4th power over 4. And then this is 2 again, and then this is 2 pi again. Yeah, so yeah, something like this. Okay, so this is actually pi rho s times R to the 4th. So this, okay, it's just, okay, so maybe for this part, okay, we try to come up with more general R first. Okay, we don't try to make it R over 3 here at the first step. We try to make it R here, and then to make the dummy variable different, okay, we make it R prime, okay, to differentiate with this R. So it turns out to be R, okay, something like this. Okay, so R to the 4th power won't cancel with this capital R. It turns out to be something like this. So finally, we would like to find, okay, Q enclosed R equals capital R over 3. Over 3 will be like pi, or maybe we try to go to the end. Okay, so E will be like it will be like integration of E dot dA times epsilon naught equals Q enclosed. Okay, so it turns out to be epsilon naught times E times 4 pi R square equals pi rho s times R to the 4th power over R. Okay, so this part is here, and then this is the very old thing. Yeah, so so this one and this one partly cancel. This pi and this pi can also be cancelled. Okay, so finally we have E to be 4 epsilon naught, and then let me see, rho s R squared over capital R. Yeah, this is it. Okay, so this is the general form where R is smaller than capital R. So if we have want to have E equals E of R equals to capital R over 3, we just plug in rho s and then capital R over 3 square over 4 epsilon naught R, which is 36 epsilon naught capital R. And then on top is rho s times R square, which is rho s R over 36 epsilon naught. Okay, then we can plug in the number. Rho s is 35.4 times 10 to the negative 12, and then capital R is 0.056 over 36 times 8.85 times 10 to the negative 12. So it turns out to be 6.22 times 10 to the negative 3. Newton per Coulomb. Okay, so this is for part C. Okay, so actually we need to compute the Q enclosed with general R, and then finally we plug in R equals to capital R over 3. Okay, so it still asks you what is R equals to capital R. So it will be easy, because we already know that Q is actually pi rho s R cubed according to question A, equals epsilon naught E 4 pi R square, and actually we have R square. So actually we also can come up with the expression when R is larger than or equal to capital R all at once. Because we actually need to graph E versus R, so it's better we know R is larger than capital R in advance. Okay, so this one we can actually cancel this pi with this pi. Okay, and then we have E equals also 4 epsilon naught here, and then R squared, and then rho s R cubed. Okay, this is true for R is greater than or equal to capital R. So finally, if we would like to find E for R is equal to capital R, we just plug in R to be capital R. It turns out to be rho s times capital R over 4 epsilon naught. And then we can plug in the number. Rho s is 35.4 times 10 to negative 12. And then 0.056. And then over 4 times 8.85 times 10 to negative 12. Okay, I already remember all the numbers. Yeah, so it turns out to be 5.60 times 10 to negative 2 Newton per Coulomb. Okay. Yeah. So this is so for the question 4 will be easy because we already calculated the total charge. So for question E, it asks you to plot the E field. Okay, so actually we have E to be rho s R squared over 4 epsilon naught R when R is smaller than capital R. According to question C, okay, according to question C, we get this. And then according to question D, we have rho s times capital R cubed over 4 epsilon naught R squared. This is true when R is greater than or equal to capital R. This is what we know from question D. So finally, we can plot the E field magnitude versus the R, the distance from the origin to the point we concern. Okay, so the middle point, okay, here is the R, capital R. This is actually 5.6 times 10 to negative 2 Newton per Coulomb. Okay, this is this point. Okay, so we can see that if R is smaller than capital R, this is proportional to the R squared. So which means that this is something like this. This is proportional to R squared. Proportional to R squared. And then for this part, proportional to 1 over R squared. Something like this. Proportional to 1 over R squared. So yeah, so this additional example, I think it is a little bit out of the scope. Actually, it is quite demand on the calculus knowledge, but just let you know that actually in the course or even in the exam, the calculation would not be as difficult as this one. Okay, it's just to let you know. Okay, if you really need to apply the calculus to calculate something. Okay, let's say to calculate the charge with a non-uniform charge distribution, even though this expression is already quite neat. Okay, it's only linear proportional to the distance. But at very least, if it is non-uniform, okay, this integration, okay, this integration cannot be simplified as multiplication anymore. You need to use some mathematics, like you need to know the spherical coordinate so that you can really compute or calculate the total charge on the sphere or on a partial sphere with a smaller radius. Okay, like here. Okay, so you calculate the Q enclosed with only a radius of capital R over 3. So in that case, yeah, actually, even though this is non-uniform, but this triple integral is not that difficult. Okay, you can still separate one by one. Okay, we call it it can be separable. Okay, the variables can be separable so that the integration. Okay, you don't need to calculate the triple integral layer by layer. You can actually separate the triple integral into 3 independent single integral. Okay, so that's the case. So